Hello there, this is Ms. Page, and in this lesson we are going to talk about how to take the graph of a polynomial function and create the function for it in its factored form by using its zeros and the end behavior. So what we're looking at is using our factored form here. Right here, which is sometimes called intercept form because factored form can show us the zeros of the function, which also give us x-intercepts. And so here we have what we would call our basic quadratic function. There are two factors that involve x, so that's going to give us an x squared with two zeros in this case. And that's our quadratic, which is a type of polynomial function. And then here we have another quadratic. And the end behavior for this one, a would be positive 1, so it would open up. The end behavior for this one, a is negative 2, so it would open down. And that's actually what we use to figure out what our leading coefficient in our polynomial functions of higher degree, whether they should be positive or negative leading coefficients, is do we have a reflection across the x-axis or not? So that leads us to talking about end behavior of our polynomial functions. So what we know is about both of these are quartic functions. And we know they're quartic functions because they have this end behavior where they both go the same direction, okay? And so this is our basic when they go to positive infinity. That's like when a is positive. And so that tells us that our leading coefficient would be a positive number. And here, when they both go down, that's when we have an x-axis reflection. And so that means our a is negative. Now, technically, a could be any positive number in this one or any negative number for that function. We're going to keep it pretty simple and just use either positive 1 or negative 1 as our constant factor a, which we're talking about here. So for our cubics, this one right here, this is when our a is positive. The right end goes up to positive infinity. And so here our a is positive. There's no x-axis reflection. Here, where it flips, and now our right end goes down and our left end goes up, that's when our a is negative and there is an x-axis reflection. So that's one way to look at it. If you kind of want a simple thing to kind of also like as a backup too is, all right, if notice both of your ends here are going down to negative infinity and your a value is going to be negative. Notice here that both of your ends are going to positive infinity and your a is going to be positive. You can also actually, to make them the same, you can just focus on the right end. So if the right end is going to negative infinity, a is negative. If the right end is going to positive infinity, a is positive. And that actually works for our cubics also. If the right end goes to positive infinity, a is positive. If our right end goes to negative infinity, a is negative. But it also corresponds to whether there's an x-axis reflection or not. So I wanted to talk about that. So if we want to create a function in its factored form from a graph, notice here it says of least degree. That means with the smallest power of x based on the given information. So we don't add any extra zeros to the problem. We just use the ones that we can see on the graph and make an assumption that those are all of the zeros. So we have to determine the zeros of the function and then make sure that we include multiplicity because that actually creates repeated factors. So from those zeros, we find the factors of the function. And again, the multiplicity makes factors repeat more than once. We want to determine the sign of the leading coefficient. So this is whether A is positive or A is negative using the end behavior. And we can just focus on the right end and match that direction of positive infinity or negative infinity to a positive or a negative leading coefficient factor. And then we'll be able to write the function in its factored form. All right, let's take a look at this problem. So make sure in these problems that you are writing your answers as a function given the name p of x. It actually tells us to name our functions p of x. We can see it's actually called p of x here in the graph too. So we are to write a function p of x. It'll be polynomial in nature. It'll be of least degree, meaning that we'll only use the given information we can see in the graph. It should be in factored form, so we don't have to multiply it out. That makes our job easier. And that we will assume that our leading coefficient, our a value, is either positive 1 or negative 1. So we won't worry about stretches or compressions or vertical stretches or compressions in this. We'll just assume that we either have a x-axis reflection or we don't, compared to the parent function for the family. So what we're looking at here is, first we want to identify our zeros. And we want to make sure that we pay attention to whether each zero is a relative maximum, a relative minimum, or just none of those. So here we have our zeros. And so we have 0, negative 1, 0, and 4. None of those have multiplicity because none of these zeros is a relative maximum or a relative minimum. So our zeros are negative 1, 0, and 4. So what we're going to do now is work backwards from these zeros to find the factors. So we use the concept that zeros are values of our variable, our independent variable x. So x equals negative 1, or x equals 0, or x equals 4. Now we're going to use our algebra to work back to create the factors. And factors can be found by taking and using our algebra so that we create an equals 0 over here on the right hand side. So I would add 1 to both sides. That gives me x plus 1 equals 0. And this x plus 1 is a factor of my function. X equals 0 is already equal to 0, which means x is a factor of my function. And then this one I have to subtract 4 from both sides, which gives me x minus 4 equals 0. So x minus 4 is a factor of my function. The other thing that I want to do is figure out my a value. Is a equal to positive 1 or is a equal to negative 1? And I do that with my end behavior. Specifically, look at the right end. That's as x goes to positive infinity. So here, y, the function, is going to positive infinity. So on the right end, our p of x, our y, is going to positive infinity. That means our a is going to be positive 1. So when we write our function, we're going to have p of x equals, we're going to have 1, that's our a value, times our 3 factors. And you should put monomial factors first, then binomial factors in any order. And in this case, since 1 times x is just x, I would simplify this to p of x equals x times x plus 1 times x minus 4. And use that as my factored form of my function. All right, let's see what's next. All right, second example for us to talk about. So again, first thing I want to do is identify the zeros of my function and whether there's multiplicity. So my zeros here are -3 and +2. But notice +2 is a relative maximum, which means that it has multiplicity. So I have zeros of -3, and then 2 repeats itself twice. So I want to make sure that I write it down twice, because what that means is that this is going to give me two factors that are the same. So now I'm going to find those factors. So each one of these zeros is a value of x. So x is equal to -3, or x is equal to 2, or x is equal to 2 again. So to find the factors, just as we did before, what we will do is use our algebra skills to create a 0 on the right hand side. So here I have to undo the -3, so I add 3 to both sides. And I get x plus 3 equals 0. So x plus 3 is a factor. Here I subtract 2. It gives me x minus 2 equals 0. So x minus 2 is a factor. Here I subtract 2. So x minus 2 equals 0. And x minus 2 would be a factor. Now I want to figure out what my a is. Is my a equal to +1? Or is it equal to -1? And I can do that by focusing on the right end. So my right end is here, and it's heading down to -infinity. So that means that we're going to have -1 as our a value this time. So that's going to give us now a function, starting with our p of x equals our a value of -1 times, this time we just have 3 binomial factors. So we get x plus 3 times x minus 2 times x minus 2 again. So we want to clean this up a little bit. The -1 factor, we generally just keep the negative, and the x minus 2 times itself we write as a quantity squared. So our final factored form would look like p of x equals negative, and then you can write your x plus 3 followed by your x minus 2 quantity squared, or it is also okay to write your x minus 2 quantity squared before your x plus 3. That's fine either way. And then that would be our factored form of our function. All right, let's see what we have next. So here is a practice problem. I would like you to pause your video here, try to write this function, and then we'll check. All right, let's see what our function should look like. So here we can see that our zeros should have -5 with multiplicity of 2 because it's a relative maximum, and then the -1. So setting each of those as an x value and using our algebra to get a 0 over here, we get the factors of x plus 5 twice and x plus 1 once. The end behavior of the right end going to positive infinity tells us that our a value is +1. And then setting that up, anything times 1 is itself, so I don't keep that 1. And then x plus 5 times itself becomes x plus 5 quantity squared. It's also okay if you wrote p of x equals with the x plus 1 first, followed by the x plus 5 quantity squared. All right, moving on. Okay, so now we have another example to do together and add into our notes. So same concept, we want to write this polynomial function of p of x in factored form, figure out if a is a positive one or a negative one, and so we want to find our zeros first. So here I have a 0 of 0, and here I have a 0 of 5. Both of these are relative minimums, so they both have multiplicity, which means that 0 is a 0 twice, and 5 is a 0 twice. So now I am going to figure out the factors. So I have x equals 0, or x equals 0 again, or x equals 5, or x equals 5 again. So since in these first two we're already equal to 0, x would be our factor. In these two we'd have to subtract 5 from both sides, giving us x minus 5 as a factor twice. All right, so we also need our a value. Is a equal to 1 or negative 1? And again, that's from our end behavior. Look at our right end. Our right end is heading up, so that means it's heading to positive infinity. Therefore, we're going to use our positive 1 for our a value. So now we can put that together and get our function. P of x equals our a of 1 times our two factors of x, which are monomial, so they should go first, times our x minus 5 and another x minus 5. So anything times 1 is itself, so I would not keep the 1. X times x becomes x squared, and x minus 5 times itself becomes a quantity squared. So my final function, p of x, would equal x squared times x minus 5 quantity squared, like so. All right, let's see what's next. All right, another example for us to do together here. So again, given any of our functions here, polynomial functions with our graph, to write the function in its factored form, we first need to figure out what the zeros are. So I find I have a 0 here at -2. No multiplicity there because that's not a maximum or minimum. 1, no multiplicity. 3, no multiplicity because those are not maximums or minimums, and same thing for 5. So there's no multiplicity in this particular function at all. Our zeros are -2, 1, 3, and 5. So each one of those is an x value, so x either equals -2 or +1 or +3 or +5. So using our algebra here, we'd find our factors. So here I'd add 2, giving me x plus 2 equals 0. So x plus 2 is a factor. Subtracting 1 here gives me x minus 1. So x minus 1 is a factor. Subtracting 3 from both sides in the next one gives me x minus 3 is a factor. And subtracting 5 for this one gives me x minus 5 as a factor. So we also need to figure out what our a value is. So is it +1 or is it -1? So that has to do with the end behavior. And again, I can just focus on the right end. The right end is heading down, so it's going to -infinity. So that tells me that my a value here will be -1, meaning there is an x-axis reflection in this situation. And so now I can put it all together and write my function. So make sure I start with p of x equals, then my a. Now this time all of my factors are binomials, so it doesn't matter what order I put them in. like so. So no repeated factors, so I can't do any quantity squareds or anything like that. And the -1 really just gets simplified to a negative. So what my function would look like in its simplest form would simply be p of x equals negative, and then my binomial factors all listed in whatever order I had chosen. Like so. All right, it's probably a practice problem next. Let's take a look. Yep, pause the video, give this one a try, please. All right, let's take a look. So here we find our zeros are -4, 0, and 2, and notice 2 is listed twice. That's because at 2, we have a relative maximum, so there is multiplicity. So setting each of those factors equal to x, or sorry, each of those zeros equal to x, and then using our algebra to get a 0 on the right-hand side, we get factors of x plus 4, x, and x minus 2 twice. The end behavior, where the right end goes down to -infinity, tells us our a value is going to be -1. And then putting that all together, the -1 becomes just a negative, and then the x minus 2 times x minus 2 becomes x minus 2 quantity squared. If you wrote p of x equals -x times x minus 2 quantity squared times x plus 4, that is also acceptable. All right. All right. That is it. This is not going to be anything we need right now. So we are all good. This is the end of the lesson, and you can go ahead and start your assignment. Have a great day.